go ahead and do the demonstration with this one. How about, let's pause the video, and if you need to stretch your legs, it's going to take me a couple of minutes to set this up. So this is called the Strength Vibrator. As basically this is oscillating up and down at 60 times a second. Now, we have not hit a harmonic state right here. We have constant constructive, destructive interference, but it's not quite at, we haven't reached perfection yet. So the question is, do I want less tension in the string or more tension in the string? Well, we can find out. Depends on what harmonic way we want. Now, one thing is that as we add more mass to this, this is going to start to move. I've had some students set up, system with 2 of these things and then the bar on it, and watch the whole thing bend. Depends on how much force you play, how much mass and there consequently weight is applied to the string. So that's the first harmonic right there. So I need to add more. I need to add more. Now, one thing you need to be careful of when this is basically the lab that you'll be doing on Thursday is you don't want this touching the ground. So the string here needs to be short enough so that it won't touch. But we do have what looks to be like a first harmonic. We have a node, an antinode, and then a node right there. And it's actually, I think, traveling in a circle there.
Surface.
Pardon?
I said surface.
So,
Yeah, I guess it would be in that sense.
So is it like a jump rope? Like there's nothing in the center?
No, this string right here is moving back and forth. The reason why you see it more at the ends right there than in the middle is because, well, when it turns around, it has to stop. So it slows down and then zips past and then slows down again. So it's traveling the fastest in the middle here and the slowest on the ends, which is why we draw it like that, because in essence, it's harder to see in the middle. Unless, of course, you're watching the video, in which case you don't see it vibrate at all.
How come the weights are getting closer to the ground?
Oh, because of that.
What? It's just slowly sliding.
And so, let's get that. Okay, it's a little bit unstable now.
Why did that happen?
Why does it get unstable?
Yeah.
The vibrations.
Because as the wave is coming down, to get the perfect standing wave, you need that perfect combination of distance from here to here, the frequency of this, and then the tension in the string right here. And if you're just a little bit off, it makes everything else just a little bit off.
So what is our lab on Thursday focused on with this?
You set this up as such, and then you put different masses on here, creating the different harmonics. And then ultimately you're going to be plotting wavelength squared versus tension, I think. I'd have to go back and check that. And then from that you can predict what the frequency of that is. And then compare it to what the manufacturer says it is, which is 60 hertz.
So can you...
Oh, that's telling you something? That's telling you the frequency?
It's not written on here, but it's based upon the frequency of our electric supply coming out of the power, out of the power stations, which is 60 hertz. Presumably in Europe, if you did this, yeah, you probably need a different machine, but it'd be 50 hertz.
Could you increase the speed of it, and would that make more different harmonics? Like if you were to increase the frequency, could you get to the 3rd or 4th harmonic, or do you change the tension to do that?
We will change the tension to do that. We don't have the capability of changing the frequency of this. Or I have not figured that out yet.
So would it be more tension gives you like lower harmonics and less tension gives you greater harmonics?
It depends what you mean by that. The low harmonics, the first harmonic, which is what this is approximately, the first harmonic, you need as much tension as, you need more tension. And as we take tension off, we'll start getting to the other ones.
Okay.
So as I take off the half kilogram, it looks like I need, no, it's still the first one, so take some more off here. And then it becomes a delicate act.
It was a second before you added that.
All right, so to do the lab really well, you know, we sort of have a second harmonic here with a node, 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 and two antinodes, but it's fluctuating, so we're just a little bit off. And it could be a matter of, let me throw a 10 on there, see what that does. And we get something a little bit more stable, just a little bit. Maybe adding, oh, I guess that was a 20 I just added. Now if we add a 10, that seems relatively stable. Now, you can get more precise by adding things of smaller mass. We have the baguettes here, so, and pennies, so you can start adding sort of part weights, part masses. All right, so let's just see how close we can actually get to 60 hertz. Now, properly, I'm going to be off a little bit for one harmonic and less off on another harmonic, or I'm a little bit high for one harmonic, a little bit low for another harmonic. And that's one of the reasons why you do multiple ones, do a graph, and that should wash out some of the inconsistencies. But we're going to just try it, because this always works well. We're going to just try it with this, just to see how close we get to 60 hertz for the frequency of that. And we'll also bring in a couple other aspects of physics which we need to discuss. All right, so that looks like the second harmonic. All right, so I need the distance from here to here, because that will be L. And as soon as I let go,
Do you need a meter stick?
I do need a meter stick. Would someone be kind enough to hand me a meter stick? Thank you, Brianna. So L. Coordination would also help. Can you bring me coordination?
I'm afraid you're all out
Is
of
it
that.
labeled over there?
So it looks like L is 91.5 centimeters. So we're on this one right here. 91.5 centimeters, but because we're cool, we want to use the international standards, so 0.915 meters.
And you'd call those a fixed end, not a node, or are they both?
They are both. This had three nodes. It had the ones at the fixed ends and then the one in the middle.
But the middle wouldn't be a fixed end. Just
Correct.
the two sides
Yep.
would be both. Middle, just the node.
Correct.
Okay.
All right, so how fast was that wave traveling? We have two formulas. So let's talk about the generic formula for how fast anything will travel through a medium. So we have, whether we're talking a harmonic wave or, you know, I just thump on the table on how long does it take for it to travel that way. The generic formula for the speed of a wave or a pulse or anything like that is we have some sort of force term divided by some sort of inertial term. And what I mean by this is force term is basically as one piece moves, how much influence does it have on the next part of it. So on the string, when one bit of the string moves, how much influence does that have on the next piece as it pulls? If we're talking sound, as the pressure wave comes out of my mouth, how much force does that exert on the next bit of the molecules that are out here, which will then pass it on. The inertial term, in essence, how much mass are we trying to move here? So as the force term increases, the speed increases, because as one moves, the greater influence on the next bit. As the inertial term increases, my speed drops, because that means I'm moving more and more mass. And it's harder to move bigger mass. Now, specifically to what's called a one-dimensional wave, now, for the purists in the group, you might look at that and say, that's not one-dimensional. The string has width and depth and length. Yes, it does. But treating this as one-dimensional, when the length is so much larger than the other two dimensions, you can treat it as a one-dimensional wave. And there's really not a loss. Or you can make it far more complicated than you need to. So for a one-dimensional wave, the speed is equal to the tension divided by the linear density. That's really not a whole lot better.
You said linear density?
Linear density.
And it's tension divided by linear density?
Say it again?
Tension divided by linear density?
Yes, and then the square root of that. Now density deals with how much mass do I have and how much space is taken up. So regular density, so this is, if someone just says density, this is what they mean by it. It's mass divided by volume. This is just density. If we are talking about what's known as surface density, it's mass divided by area, because if it's a surface, you don't have a volume of a surface, you just have an area. So this is surface density. So we have mass divided by volume, mass divided by area, linear density. So want to take a shot at what the formula is?
The distance, so like meters?
Okay, mass over length.
Okay.
And so that's linear density. L for length.
Is that a sigma?
That's a sigma. Yeah. So as part of the lab, you're going to need to figure out the linear density of the string. And by doing that, you'll use a balance to find the mass. And then you'll take some sort of length measuring device and measure how long it is, and divide. The trouble with the lab, I found that the biggest issue that students had of getting really horrible results was finding the linear density. Because if the balance is just a little bit off, that can really mess it up. Because the string over here, unless somebody has messed with it, I think this is about 3 meters of string here, and its mass is about 3 grams. So if the balance is a ½ gram off, well, you've already introduced 16% error right there. So I will spoil this for you, and I still want you to do it on Thursday, but for that piece, and I'm not saying that the length I measured was correct, it's just this is what I got. I had a mass of 0.00316 kilograms, or 3.16 grams. The offset was 0.00000 kilograms. In other words, when I set up the balance, I made sure that the line was perfectly lined up with the indicator. That it was not just a little bit off. I tried very hard to make sure that it was lined up. And the length I measured 3.0485 meters. So therefore, the linear density I would take the mass that I measured minus the offset, which is simple, and then take that and divide by my length. And if someone would be kind enough, all right, this number? Okay. What would the units be?
Kilograms over meters?
Yes, because we took mass in kilograms and divided by length in meters, so it's kilograms per meter. Now the tension in the rope, well, if I think about this, I had this mass sitting right here. It's in equilibrium, close enough, so that the weight of it should equal the tension, because I have two forces acting on this. I have weight acting down on this, and I have tension pulling up on it. If it's in equilibrium, they are equal. And so, I basically have that mass there, I have weight acting down, I have tension acting up. And so my weight, mg, and the mass, I have a 10, a 20, and a 200. So on the surface of it, it's 230 grams, 0.230 kilograms. I am going to pretend that the manufacturer printed that correctly and that they don't have a mass different than that. In the video, when I was trying to get incredibly precise, I made sure I put it on the balance. And then G, this is a physical experiment, 9.798 meters per second squared. We end up with 2 point something.
2.25354.
25354.
That's correct.
Units.
Newtons.
So that is the weight that was hanging on the end of the string, and therefore we assume that is the tension. One thing that we are ignoring was the actual weight from the string itself, or we took the mass of the string into account with the linear density here, but we did not take into account the weight of the string. Now, it doesn't make a whole lot of difference at this point. If I was going for a higher harmonic, it starts to make a difference. And that's one of the tricky things about the lab is you try to get the higher level harmonics. Because you have so little mass on there, the mass of the string or the weight of the string starts to have an effect. So, therefore, the speed of the wave, based on our measurements there, would be the square root of our tension, 2.25354 newtons, divided by our linear density, 0.001035 kilograms per meter. And we end up with a speed of attention builds.
Not in the question though.
What?
I said not in the question though.
True.
46.628.
26.60.
I said 46. 46.62.
Let's start over again. What is it? It's
46.
46.
Yes. 62. 81. Do you want all the numbers?
That's probably good enough.
Okay.
Units?
Meters per second.
I hope so. Should be meters per second. All right. It doesn't tell us the frequency yet, but we know how fast the wave is traveling. But I said before that we have two formulas for speed. That is one of them. The other formula for speed is basically distance over time. So let's get rid of this stuff here. I'm going to pretend that one of these markers will make really nice marks there. So speed, distance divided by time, that has not changed since chapter 2 or 3. If we go back to the definitions, the time it takes to create one wave is the period. So let's take a look at just one wave. How fast does that first wave go? Hopefully the same speed as all the other waves. So the first wave travels in a certain time period. T, the wavelength. The wavelength is how far it travels in that period. And so this is just wavelength divided by the period. Taking the extra step here, that's the wavelength times 1 over the period. And what's 1 over the period? And as you're thinking about that, I will close the door. So what's 1 over the period?
That's just frequency.
So this is just the period times the frequency. And so our speed here should also be equal to the wavelength times the frequency. I think I misspoke just then. It's wavelength times frequency. This is the equation when I talked about in the video about there's more than one technical symbol used for frequency, and the other one is the nu, which looks a lot like a V. This is the formula I've tried to find in order to figure out what the nu and the V look like in the font that that textbook is using. Because some textbooks, V looks like this, and in some textbooks, nu looks like this. They are really hard to tell apart. So, wavelength. What is the wavelength of our second harmonic there?
Just the length of whatever. Just the length.
Yeah. Because the second harmonic is one wave. So, 0.915 meters.